Hello, everybody. This will be an interesting talk. I promised my favorite code examples about C++20. C++20 is pretty new. Every week we have a new compiler version out of the major compilers. Every week I learn something, although I have seen all the features right now, I hope. And so this talk is constantly changing. And so this is a version of November 10th, 21. And let's see whether you like what I like. So the talk will roughly talk only about how to print elements of a range. But there are so many interesting things to discuss. I think that's enough. So let's see where we are. We have here a data structure, a coordinate with three values, x, y, and z value. Let's use it. Well, let's initialize an array with some coordinates. Since C++17, we don't have to specify the element type and number if we initialize with the same type. And let's sort them, and let's print them out. Okay, and how do we print? Well, let's print it the old way, not the C++20 way. Here's nothing from C++20 yet. So let's use a template. Let's print the elements of the past array, iterate over the array, and print out the value. Good. So the first thing we can improve with C++20, as you might have heard yet, is instead of writing that this is a template for type T, you can just write auto. By the way, it's still a template, and it still follows the rules of templates. For example, you have to put it in a header file. And then we can switch the sort algorithm. So before C++20, we pass begin and end as usual when we pass ranges. So now we can just pass the range as a whole using a subnamespace called ranges. Okay, so but for sorting, we need a way to compare the values in this data structure. And what we usually have to implement is the less than operator for that, or we need to set sorting criterion for to pass to sort as an argument. Well, we have something new here. You might have also heard about this. That's the spaceship operator. And the spaceship operator is responsible for the comparison operations, well, at least for 4 of them. But if you declared with equals default, even for all 6 of them. So by that, you enable comparing coordinates with all the 6 comparison operators, checking for equality and relations and ordering. And it uses, by the way, the members x, y, and z in that order. So we sort according to x as a first criterion, then to y, and then to z. And this will also support const expr and no except and type conversions. So that's all you have to do. And then, of course, we need some output support because we print all the elements and the elements are coordinates. So we need an output operator. Well, an output operator, you still have to implement the usual way, which in this time is using a hidden friend, so a friend function inside a class or data structure. And so we want to print it out that way. So how do we do that? Okay, we could print out x, y, and z coordinates and stream them out to the output stream and then stream out a slash in between. But we have something new. And something new we can use here, and that's format. std format is a library for output formatting so that we can specify field width, alignments, etc. And let's use it just that way. That's pretty simple. Print out the 3 values as passed here as additional parameters with a slash inside. And here we could do a lot of alignment tricks, which I didn't use here yet. Okay, so wait a minute, I have to organize my screens a little bit better. else can we do? Well, this print function does support ranges, but in the declaration, according to the declaration, it can take everything. So we can restrict that by saying, okay, let's use only ranges here, ranges where we can read values from. And for that, we have concepts, standard concepts, so that are constraints about template parameters. Remember, auto is here just a template parameter, a generic parameter. And this is a so-called type constraint. So we constrain the parameter here that you can only pass input ranges. So if you pass an int, a good compiler might say, oh, that does not fulfill the requirement that the argument should be an input range. Good. Okay. Oh, let's skip the first coordinate, by the way. That's another thing we have with C++20. So let's skip the first element. Oh, that's easy. Take the array and drop the first element. Well, what we create here is not a new container. It's just skip the first element while iterating over the elements. So we have here a mechanism of lazy evaluation. We create a view. A view refers to the original array that says, well, if you want to iterate over my elements, skip the first one. And so the moment print starts in this range-based for loop to say, okay, let's iterate over the elements, the first begin goes to drop goes to the array and says, give me the first element, and then drop says, oh no, I give me the second element because I want to drop the first one. And then, so from this point of view, this view gives you as a first element the second element in the array. And that means we print not the first element, which would be 0, 0, 2 here of this array. Okay, so these are all cool things you might have seen already coming from C++20. Range support, you can use ranges as a whole. You can pipe ranges into views, so to filter them out, etc. You can put constraints, etc. You can use auto instead of template parameters. So things like that, and to print out via format, to define the comparison operators, you have the spaceship operator. So, but let's look into a little bit more interesting examples. So first of all, as usual in C++, not everything works as smooth as it looks like. So if I take this program you just saw, remember, let's print all the points, drop the first one, well, after they have been sorted, and let's use this print here. Oh, let's use a filter instead. So instead of dropping the elements yet, let's use a filter. But a filter is a predicate, well, and in contrast to drop, it looks to each and every element and says, oh, I pass this through. If you ask me for the next element, I give it to you, or I reject it. So this filter is a little bit trivial. It says, yeah, I accept all the elements. I always return true. But here there would be your condition, what elements should be filtered out, or what elements should be filtered through. But there's a problem now. This code no longer compiles. There's a compile time error. What the hell is going on here? Well, there's a problem, and the problem is the following. We have here a print statement that takes a const reference to whatever we pass. And there's a problem with some views, because some views have a state. And that means while you iterate over the elements, they modify their internal data. And filter is one of them. So if to iterate over a filter, the view can't be const. But we made a const here. So therefore, this code will not compile anymore. That has interesting and dramatic consequences, I think, for C++ as a whole. So here you see some filters work, like drop work, but others don't work. Some not always work when they are const. For example, for drop, just drop, it worked because we were iterating over an array. But if we would iterate over a list, it would not work to pass it as a const by const reference here. So in general, not all views support iterating over the elements when they are const. Some always, some sometimes. And for that, we have to change this code. We have to say, okay, let's not make the parameter const. Well, we could pass it by value. If it's a view, it's cheap. A view is cheap to pass. So this is a view. We pass finally a view to this array. But we might also want to use this print for ordinary containers, ranges, which are expensive to copy. And as a consequence, we should not pass by value, at least not in this case. So there's a solution for that. We have a type that says, let me pass something by reference without becoming const, and a reference that can refer to everything. And because a non-const reference cannot refer to temporary objects, that's a universal or forwarding reference. It's usually, it was introduced for perfect forwarding, but more and more it turns out that we need the other flavor of this reference, which is to universally refer to something by keeping all its attributes. So not being const is one important point here. So therefore, I tend more and more to come back with the old term we had, universal reference, because forwarding reference sounds like we are using forwarding here, which we don't use here. We don't use std forward here. It's just a universal reference. And there are two ways to do that. You have to use a template parameter with 2 ampersand or 2 ampersand with auto in this syntax. So yeah, and we can still qualify. It has to be an input range. So with this declaration, everything works fine again. And you can, of course, apply more interesting filters here. Good. So good things and bad things happen when you apply and use C++20 and the features of C++20. Let's improve the whole stuff a little bit. Look at this. Look at this here. This is a range. So what is a range? A range is something we can say that as, well, historically defined by begin and end. And begin and end usually are iterators. Well, raw arrays are supported by using pointers as iterators, which provide the same API and therefore can be used as iterators. But there was one interesting restriction we had before C++ in almost all places in C++, which is begin and end of such an iterator had to have the same type. So a begin and an end iterator had to have the same type. But there are nice applications if this is not the case, if the end has a different type than the begin. Here's one. Look at this. I want to iterate over these points, and my end is just a specific value, not an iterator at all. It's something I can use a little bit like an iterator, but yeah, let me define a range that goes from begin to this value. This should be the end. And let's define it as a template parameter. And of course, this is a type. This is a declaration. This is the end value of, and the value is initialized with this value. That's a template parameter. That's a fixed end value we are using here. So this means let's iterate for all points until we come to this end. how can we implement such an end value? People have done that before C++20. And you can, for example, do something like this. Here's a data structure, end value, that's my type. It's templified by the value that defines the end. And then, what else do we need to deal with that? Well, let me first say that there's a terminology, a new term introduced with C++20, which is the end iterator in general is called now a sentinel. So we always iterate with iterators until the sentinel, which is a synonym for end iterator, but may have a different type. And that could be used like such a sentinel. So how do we define and implement this sentinel type? Well, that's all. That's all you need. You need nothing else. What we define here is, let's compare my value with an iterator. That's here. The argument is just some iterator. And yes, we have the end value. If we compare with an iterator, we have the end value if where the iterator points to has the same value as the initial value passed to here. Now remember how this range-based for loop works. So first of all, there's a remarkable thing, that is the range-based for loop already supports begin and end having different types. That was introduced by C++17, by the way. And but internally, please note that internally the loop here initializes an iterator and says, I'm iterating until I am at the end. So why I'm not at the end. So some code here internally is why my internal iterator is not at the end. Now, what is the end? The end is this. The end is this object. This object has an equal operator. And here we see another feature of the new spaceship operator and all the technology around it. We have new support to rewrite comparisons. So we have defined how to compare an end value as first operand with something else as second operand. This is comparing not equal, and the order of the elements is different. But there's a new rule that now this can be used, because if the compiler cannot compile this, it will use this instead and try this instead. So it tries, is there instead of a not equal operator, is there an equal operator defined? Yes, we have it. And is it even defined for the opposite order of the operands? Yes, and then we negate the result, and that works. So therefore, this is enough to make this work. And what we do here is we create simply an object, a range starting with the begin and ending with this element. Yes, obvious questions will be, what happens if I don't have such an element? Yes, we will iterate forever. So that's, you should only do that if you know that this element is inside. But there are other ways to do that. We could, for example, here pass as a runtime argument the array, and also here compare the iterator with the end of this array and with this value. So whichever comes first, that's not a big thing to implement then in addition. Okay. Here's another remarkable thing. I don't know if you see that. We use here auto. We use here template parameter. The template parameter is a value. This is a non-type template parameter. So what is the type of this? Well, it's a literal type. It's a data structure. And that's new now. We have a lot more support for non-type template parameters now in C++20. In fact, if you have a template, generic code templified for a specific value, the value can now also be a floating point value and a literal type, like here, which includes that you might be able to have support for string literals and lambdas. Yes, lambdas could also be template parameters now because, yeah, they are. They can be literal types. They can be data structures, and that works. I have some examples in my book about that. I have not yet a very useful example to use a lambda as a template parameter, but I'm pretty sure we will find a lot. Okay. So how many features are on this slide? Okay. Concepts, standard concepts, NTTP parameters, rewriting of the equality operator, the spaceship operator, STD format, ranges take ranges as a whole, so passing ranges as a whole instead of begin and end, helper types and views like subrange, drop you have seen, filter you have seen. These are all views, temporary created views. Here the view is, let's define the range from to this array up to this value. That's my first example. Oh, we have something else. The chrono library was extended. Oh, we should try this with chrono. Well, something like this. Okay. Let's take again my print function. I accept an input range, arbitrary input range, not making it const, so I can read elements from that of any type. Let's pass something different. Let's pass an array of dates. Cool. The chrono library extension for C++20 now supports calendar types, a lot of calendar types, very type safe, with interesting behavior. You might have seen the keynote by Howard, I don't know, 3 years ago or so. Here you see some ways to define such a date. So this is today, the 10th of November, 2021. There are other ways to define a date. This all could be variables, not only constants. And please note that we here use an operator already. So we create here an object of type day. Then we use this operator to combine it with a month. The result is an object of type month day. And then we combine it with a year with this operator. And the result is an object of type year, month, day. And that's also here. It's just that the order is different to support the 3 major formats we have. So we can start with a year, then the next is always a month. Or we can start with a month, and we have predefined values for the common month we have, so like November 1st, 2021. And so I see you can ask questions at Q&A. From time to time, I look there, but I might most of the things answer at the end. But so unless it's just a direct question for the understanding. So let's take the dates, let's sort them and print them out. Okay, now we know these are dates. Okay, well, let's iterate over the dates, which are days, more or less. Oh, let's print them out. That's new. That would not compile in C++17. We have now a default output operator for every duration and time point and other chronotypes. So by default, you can always see something. You don't have to add units or whatsoever. So it's like this. This is a day we print out. The usual format we have in IT, which is with the slashes. For all the other dates, by the way, we use slashes, but here this is very common in IT as a default value. Yes, you can change that with the format command. Oh, I don't like Mondays. There's a song, you might know that. So if the weekday of this day is a Monday, let's print that out. Oh, that's a Monday. That's not. Let's schedule meetings. Okay. Take this as a local date type plus, so we have a day here, and then we have now to add 12 hours to that. So now we have a date combined with an hour, and that's some type that works, some time point type that works fine. Okay, let's apply to the current time zone. That's a time point associated with a time zone. And then let's iterate over some other time zones like Europe, Berlin, and America, LA, and print out the meeting dates. So like here, print out, well, here you see format again, the format library. The format library supports extensions for user-specified types. We have done that for the chrono library. So you see here, the format that is supported here says, oh, let's take here the next value, the next parameter, and here some formatters, meaning here in this scenario, the day in this format and the time and the time zone, the abbreviated time zone here, which might look a little bit different depending on your local machine. Maybe GMT -8, maybe your time zone in LA depends a little bit on the platform. Yeah. Okay. Good. So we have support, all the support we have seen now, of course, also for the new chronotypes. Yeah, works fine. And then I thought about this example and said, oh, wait a minute, let's look at the example I had. And can I use this at compile time? How much can I use at compile time? So look at this. This is a compile time defined array, some values. And for some reason, I have to merge some other values. As you see, the other values are also known at compile time. So think about this as a framework. There's user code, there's framework code. They have their values. The framework has other values whatsoever. And so all are known at compile time, but at very different locations of the source code. Okay, so how would we implement a function that merges these two values, 42 and 4, and that's a variadic number of arguments we could take here, pass here, to this array, and then come up with a resulting range that we can use and pass to print and do all the funny stuff we have seen before. Well, okay. Merge the value. Let's see later what the return type is. A traditional way would be to take a template. So template parameter for the collection we pass in. And then an arbitrary number of values. We use variadic templates here. So these are multiple types and multiple values of these multiple types. And to support move semantics, we use 2%. So we have used universal or forwarding references. Just in case, well, here we have int, we don't need move support, but you never know. So let's initialize a vector with these elements. A vector declared with the value type of these elements, and then initialized with begin and end. So you might say this is, some of these things are not necessary, but be careful if you use class template argument deduction here and you don't specify the type. Here you would have two elements, which are two iterators. So you have to specify the type, or the other option would be, in this case, to use parentheses instead of curly braces. One of the nasty areas in C++ where we have different behavior, whether we use for initialization parentheses or braces, but that's a different story. So let's initialize the vector with all these elements, and the elements are use the value type of the parse container type elements, the value type of the container. Here are, as you probably have learned, the hard way is, because all your compilers tell you is, let's use type name here, because this is a member, a type member of this parameter. So now let's merge all these values. I don't know how good you are with C++17. That's a fold expression. So this is a commando as a comma separated list of statements call pushback for all the past values. So that way we call pushback for all the past values using move semantics. So we forward the elements into the collection. Well, let's sort them. Okay, and let's return the collection. So what we have done, whatever you gave me in, internally I create a vector initially with these elements, and then I added 42 and 4, sorted all the elements and print out the elements, and yes, that works. If you iterate over the elements, you see this result. That is code that works. Okay, a few things about this. So first of all, this is so far code not using anything of C++20 again. So how can we improve it? And so let's go through it step by step. So first of all, this type name is no longer necessary. You can skip it. That in a lot of places where it's obvious that the type name is a type, that the type member is that the member is a type, you can skip it. There are some special rules where this is not possible. Yeah, so it's a little bit funny because finally in Visual C++, they really require the type name, and now it's no longer necessary. Okay, so that's possible. Good. Then we can here the sort. Let's apply the usual things we have seen in the code before. Okay, look here, sort. Let's use a sort for just sort all the elements in the vector, the ranges sort. And let's here, instead of taking template parameters with the name, let's use auto here. So const auto reference for the range, and to have perfect forwarding and move semantics, universal or forwarding references for the past arguments, the values you want to copy or move into the collection, with auto to ampersand, and then dot 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 to signal we have multiple elements of that. Once again, this code is equivalent to this. It is still a template. It follows the same rules. The difference is that we have no specific name for the types anymore. That means instead of using the type, we have to use decal type of RG, or here decal type of vals, whenever we need the type of these elements or the template parameter of these elements. We don't have a name for that, so we use decal type here. That's interesting because that means that in this case, I would probably prefer not to use auto here. I would probably still use that one because I need these two names, T and args. So that would be my code. Okay. So the only improvement we have now is use rangeless sort. So let's change the declaration here. Look at this. We have an std array initialized, but now let's switch to a raw array. And the code suddenly no longer compiles. So this code is not as generic as it could be. Yeah, so can we improve that? Yes, because in C++20 we have a lot of support to program ranges, not only to call algorithms for ranges and have something else. We have a lot of support to implement code, generic code for ranges. And so what do we have to modify so that this compiles? Well, we have to declare it like that. Well, there, as usual in C++, there are many ways to do something, but this is one way to do it. So this is, let's pass ranges begin and ranges end. Look at that. Here we call a member function. Of course, a raw array has no member function begin and end. Here we use ranges begin, ranges end of this range. And that's what we call a customization point object. That's an object, by the way, that's no longer a function. And this supports all ranges and views. It has no ADL issues. Why do I have to say that? Because there's also an std begin and std end, but they have problems in some situations. So we fixed these problems with these new helper utilities in the ranges library. So please prefer them over std begin and std end. There are even more things fixed. For example, we have const issues with c begin and c end. Constness is partially broken, well, or no longer propagated for views, so that c begin and c end is broken in C++20. We will fix that with C++23, unfortunately, only. Yesterday there was a vote to put it in the fix. And but this fix will only apply to std ranges c begin and std ranges c end, not to std begin and std end. So please prefer these in ranges-specific helper functions to deal with generic code dealing with ranges. And here you see another helper that is in ranges. Give me the value type of the range that is programmed in a way that you also can use raw arrays there, which don't have a member value type. Okay, by the way, this is not perfect. You should improve this because this requires, because we initialize a vector, this requires that begin and end have the same type. There's a problem with the traditional compilers, containers, that they require begin and end to have the same type. And if you initialize them with a range, and to do that, and you have seen one example where we had different types. Remember the sentinel end value we used. This would not compile here, but there's a way to come with that. You could use a helper view. It's called common. You can pass through this view to iterators, and they harmonize the iterators, give them a common type, and then this code will compile. I don't have an example for that because otherwise I would have needed 1 hour more to start the talk. Yeah, but you will find examples in the book how to do that. So that way we would even support in this merge value algorithm iterator and sentinel ranges. So, and now I have said, wait a minute, everything is known at compile time. So can we somehow compute everything at compile time? Okay, const expert is a way to say that, though. Oh, let me compile this at compile time. Let me try to compile this at compile time. Surprisingly, this code works, although we need a vector. Because a vector now has a couple of const expert support. Almost all member functions have that. And but here we return the vector. We create a vector and we return it. And here it is used at runtime. So here are the news. You can use now vectors at compile time, but you can't use a compile time vector at runtime. Okay, so we have support, in fact, for memory allocation, which vectors use. And by the way, we also have compile time strings now, but you cannot propagate these strings and vectors to runtime. So if I try, this code works because finally here at runtime, we make this call and we create a vector. If I would say here a const expr in front here, this would not compile. Well, we also have a new keyword. The new keyword says it's not optional whether we do it at compile time or at runtime. Let's only allow to do it at compile time. That's called consteval. And consteval says this is a compile time only function. And yes, this function is fine. It works. It compiles. This is a valid compile time only function. Let's initialize a vector. Let's push back some elements. Let's sort them. Let's return the vector. That's okay. The only problem is, now we are required to compile this at compile time. And then we want to use the result as runtime. And that's not supported. So what could we do? Well, first of all, as a proof that this in principle works, look at this. If we would just compute the resulting size of the vector and then take the return value here, and this is not just the vector we return, just its size, that would compile and work fine. So, but of course, I was thinking, I want to merge all these values at compile time, creating no runtime computing at all. Well, we can't propagate a vector, but we can propagate an array. So we can, at compile time, take the vector, initialize an array. Now, the question is, what is the size of the array? Well, it's the size of the range, the given range, plus the number of additional parameters. So that's the resulting array. Please note we use here s size. That's signed size. That gives you the size as a signed value to get rid of these strange warnings that we compare signed values with unsigned size values. It's also new. So let's copy now all the elements from the vector into this array and return this array. And that is good. That works. That compiles. This code compiles. The only compiler you can try it out now is Visual C++, but it works. This is working code. And yeah, this is the output. So we have, it's guaranteed that this call is done at compile time, initializing this value. It could be const expr here also. And yeah, we have initialized an array with the values of the original arrays merged with 42 and 4 and sorted. Good. A few hints here. First of all, you might say, can I initialize the array here with the size of the vector? Well, that's not supported. Sorry. Before I come to that. Again, now, as we use now compile time computing only, let's get rid of all the move semantics and for perfect forwarding, because we only have values and it's all computed at compile time. So we can simplify code like this now. because at compile time, it doesn't matter. This has no impact on the runtime of the program. So, and now we come to the problem. Can I use the size of the vector to initialize its array? No, you can't. That's interesting. We have a difference between compile time values and compile time runtime values. So this is a compile time value, the size of the number of the additional elements, and vectors and arrays need a compile time value here. And so what you have to pass here is something known at compile time. Unfortunately, the size of the vector is not known at compile time, although this code is only used at compile time. We don't have support for that yet. We could, but we were very late with this feature, and we were a little bit careful. So this will not work. This will also not work. So you could say, okay, let's initialize a value here, because here now the compiler will say, but this is not a compile time value, although it's computed at compile time. You see the point? So that's a little bit of an unfortunate restriction to this code. So I thought a little bit, can we do it? Can we do it somehow? Can we somehow return and use the resulting size of the vector and return it to the caller here at compile time? Well, yes, here's a trick. And maybe there are better tricks. This is just where I was right now, 10 minutes before I started the talk. And so let's compute here with const expr the size we want to have. So which is the size of the given range and the additional values. That's a maximum size. So let's initialize an array with the maximum size we could have, which is the number of elements in this array plus the number of additional values we passed to this. Then in this case, now let me remove duplicates here. So just that we see that we not necessarily return a vector that has just this sum as resulting size, because here this 4 here is twice then, and we only want to have them once. So it would mean that depending on the values we merge, we have a different size which we return. So unique copy does that. This is the unique copy version of ranges, passing the range and the begin of where we copy the values while we removing consecutive duplicates. And now let's return two things. The array and the size. And the size is here, the unique copy gives us indirectly the position of the end, and we have to deduce the position of begin, and so that way we have the size. So this returns array and its size as a pair. So what we get here is not just a collection, it's an array and a size, because the array might be too big because we have removed duplicates at the end. So what can we do? Well, use a view. We have so many views. So here's one view. One view is give me the begin of some range and a number. Counted does it for us. And by the way, counted is implemented in a way that it creates a different type if the elements are in continuous memory than if they are not. So, so that means counted gives you the best performing runtime thing you can use here. So counted takes the begin of the array. So that's in the pair, the first element. And here, the second element is the size. Yeah, I should probably use here in the next version structured bindings to have better names for my elements in the pair. But I hope you see the point. And voila, this is the result. This is, we have a compile time collection. This collection is passed to a compile time function. initializing a vector and dealing with it, not knowing what is the resulting size because we sort and we remove duplicates. But what we can return, we cannot return a collection with that size because the resulting size is a runtime value known at compile time. For the size, we would need a compile time value, and we can't propagate a vector to runtime. But we can use this array trick with a size. So we have the array and say, but only the first n elements are valid or should be used in this array. And that is the way you can use it right now. So we now have here, the array, by the way, has 10 elements, 1, 2, 3, 4, 5, 6, 7, 8, 9, about the, or 9, no, yeah, 9, I think. And the 4 is, we have twice, but because we initialized this range, this view, we can use that. And now we can here use our print function that deals with the elements. And yeah, I could put together everything and say, oh, and these elements are chrono types, because chronotypes are compile time types if the values are known at compile time. And that would also work. But that's something I give you as an exercise. And by the way, if you do that and try it out, don't forget these two empty curly braces. Well, this is code that compiles with Visual C++. The latest version, by the way, it does not compile with the C++20 flag. You have to use a C++ latest flag. If you don't do that, you return from compile time to runtime some values not initialized properly in this array. And that is at least an error with Visual C++. Not sure about whether this is an error according to the standard or not, but it's a good error in any case. So please don't forget to pass empty curly braces here so that all the elements in this array are guaranteed initialized because we pass them to the runtime. That's it. So as I told you, just printing some elements. Maybe we compute them at compile time. And you have seen a lot of different features here in this talk, I think. Not all, we have a lot more, but you have seen that. So that's it. Hope you enjoy. And let me now go through the questions you have. Okay, so the first question is,
thanks, Nico.
Yeah. So should I continue, Marco? Yeah.
Yes, I give you assistance if you need. Thanks for the talk.
Okay. So where does it get the count zone from in Chrono? Okay, let me go to the Chrono slide. Well, current zone is supported by the operating system. So you need support for this library. You need, obviously, you need support by the operating system. So to detect what is the current zone, also the operating system has to have the ANA time zone database to know which time zones are supported. You can't use here any combination that's predefined combinations. So you can't use Europe and Munich. I think that's not a valid option. So these are the official names in the so-called IANA time zone database, which are supported. And we have an API for that. So we either require that the operating system has the current version, including offsets of time zones, etc. But we even have support that these time zone databases could be updated in case, I don't know, some country decides that's daylight saving time or summertime, as we say somewhere in Europe, it's changed a little bit. Things like that happen. Usually they happen with the operating system update, but we have in C++ full support. So we could even run C++ programs 30 years, including updates for time zones. That's there. Okay. So slide 20 or 21, does decal type RG not give a const ref type which won't have a value type member 2021. You might be right, and I didn't try it out. Wait a minute. Range is a reference. I have to check that. Yeah, you might be right. Thanks. So in that case, the code would become even more complicated, so that we had to say remove CVREF from this RG parameter. On slide 19, you speak of compile time vector. I thought compile time dynamic memory allocation is only permitted if it's delocated before leaving the time context, but you never call in a compile time context. I think that was answered later, or I think, yeah. Yeah. I think I answered that. Yes.
I think so.
In which case would you prefer to code the printing logic directly into an operator less than instead of using formatter, which is the customization point for std format? Okay. Not here. When we had introduced here the output operator for this type, yes, there's another alternative. We could say we define a formatter for our own type. That's pretty straightforward, pretty easy to do. The simple things you can do, you have just need a helper function, create a string out of this data, and then pass it as a so-called formatter to format. And then you have support, and we could just call format for a coordinate C. When should you do that? When not? I don't know. If you need it often, as usual. If you need it often, and if you have an obvious implementation, so those who design this data structure might come up with a standard formatter to do that. Yes, I would see. I support for more and more types. We will see that in future. Depending on the success of format, but I use it already a lot, and I really wait eagerly that GCC does support format. Unfortunately, it doesn't do it yet, and because it's so much easier to print data around with field width, etc. So yeah, I have no clear answer on that. If it's worth it, if it's worth it, it depends. Consulting answers are always, it depends. Yeah, could you please publish the code? Yes, I will do. I will tweet it, and I will publish 2 examples or 3 of this code. Yes, please look at my Twitter account. I will. Yes, of course, this is nice to do. So you will see the example with the runtime computing. You will see at least the final example with Chord, and maybe we had 2 other interesting versions. Please look at my Twitter account.
I think, Nico, you can take the last 2 questions that are new,
yeah.
And then we can move to the lounge. We have a room for you. It's called track C, so is the Q&A track C in the lounge. But okay. We have two last questions here appearing in the Q&A.
What's a real-world example where the complexity of writing something like the compile time list merge is worth the reduced runtime? I have no idea. We are discussing that. So the reason we have compile time computing for vectors is we are preparing reflection. We are preparing reflection, which will come with C++ sooner or later. And reflection means that at compile time, we create containers which list, for example, the members of a data structure and the names and the members of the parameters, etc. And we decided that we want to use vectors there instead of creating our own internal compiler-specific helper type. And so that's why we have this technology. as well, I think the example I gave you is as close as it could be. I mean, think about some more complicated computation. My usual example of compile time computing is hash values, compute hash values at compile time. So there are some things you can do at compile time, but yeah, maybe sometimes people think too much about it. Yeah, but yeah, let's see. We will find out also here. And
so last one, Nico, is
how the
from
speech?
Andreas.
Yes, Andreas. Oh,
yeah, because well, we can take the last two. We can take the last two. One because basically you are sorting the questions from the recent ones.
Oh,
but it's you can answer both. You can answer both. We can then we move to the lounge.
Yeah. Is it possible for future versions to allow compile time vectors to be transferred to runtime? Yeah, we are discussing that. The problem is simple. A compile time vector type might not be a runtime vector type because the runtime vector type is part of the library. Now, if we exchange the library, you have a different type for vectors and strings than the type you had at compile time. That's our major problem there. And I have no idea where the clarification and discussion is about this issue. That's it. Thank you very much. So
nice.
I go Nico. Now. Yeah.
You go now to the lounge, and the name of the table is Q&A track C. So the people can follow up with you. And okay, so thanks a lot. Thanks, Nico. Thanks, everyone. Enjoy the rest of the conference, and see you these days. Cheers.
Thank you. Bye.